In this work, we present how a VR user can interact with real-world objects through style-aware augmented virtuality embeddings. The challenge to find a real-world object in order to interact with it is a well-known problem for VR users. Even worse, unintended interaction can potentially be dangerous. Removing the headset or using a pass-through solution to solve these problems disrupts the immersion of the VR application. We present an augmented virtuality pipeline that enables the user to interact with real-world objects through stylized representations, which match the VR scene and thereby preserve immersion. It consists of 3 stages. First, the object of interest is reconstructed from images and corresponding camera poses recorded with the VR headset, or alternatively, a retrieval model finds a fitting mesh from the ShapeNet dataset. Second, a style transfer technique adapts the mesh to the VR game scene in order to preserve consistent immersion. Third, the stylized mesh is superimposed on the real object in real time to ensure interactivity, even if the real object is moved. Our pipeline serves as a proof of concept for style-aware AV embeddings. For the user of a VR application to be able to interact with a real object, its digital representation needs to resemble at least its core structure. This can be achieved with 3D reconstruction techniques that capture the shape and appearance of real objects, or by querying a large 3D shape database and finding a matching representation. ShapeFindRR is a proof-of-concept implementation of in-situ mixed reality input for shape retrieval of physical objects. It enables the use of textual or spatial search queries such as mid-air drawn sketches, tracings of physical objects, or a combination of prior search results with sketched features. This approach, like all retrieval methods, requires a sufficiently large dataset. While we also implemented an image-based shape retrieval process, we propose to use a multi-view image-based 3D reconstruction method instead, in order to achieve high geometric similarity. Specifically, we train a neural radiance field model using the fast technique of instant neural graphic primitives that we accelerate by direct camera input from the VR headset. To preserve the user's immersion, the reconstructed mesh must be adapted to the style of the VR scene. Artistic radiance fields applies the style transfer directly on the nerve scene by using a nearest neighbor-based loss that captures style details. While this method ensures consistency when images of the scene are rendered from different views, it only takes images as target modality and requires more time than the text-to-mesh model, which we chose to adapt our reconstructed and retrieved meshes. The final stage of our AV pipeline ensures that the reconstructed stylized mesh is aligned with the real object, so that the user can interact with it through the digital representation. An object instance relocalization model trained on the RIO scene dataset, which contains indoor scans with annotated 3D poses, could be used, but we implemented a detection model trained on the objection dataset, as it contains an order of magnitude more samples. All that the user of our AV pipeline needs to do in advance is to capture the object of interest from different viewpoints. The corresponding camera poses that are required to train a nerve model are recorded simultaneously through the tracking process of the VR headset. If a multi-view recording is not possible, for example due to movement restrictions of the user, the alternative retrieval approach should be considered, which only requires a single query image. To improve the quality of the reconstruction results, we apply a pre-trained U-squared-net model for salient object detection to remove the background of the input images. Then we train a nerve model using the instant neural graphic primitives technique and the marching cubes algorithm to generate a mesh in a matter of seconds. The pre-processing step of removing the backgrounds improves the geometry of the resulting mesh, which has fewer undesired artifacts and becomes smoother, as can be seen especially on the seat surface. Finer structures like the armrests may be removed along with the background in some of the images and thus be missing in the final mesh. More traditional 3D reconstruction techniques, like LiDAR scanners or the call-map algorithm, manage to reconstruct the armrests, but fail to do so with dark-colored areas, resulting in holes in the back of the chair. Call-map also misplaced some vertices at the top of the chair, creating large spikes. While the LiDAR scan achieves the highest shape similarity, our approach does not require an additional depth sensor and sufficiently captures the basic geometry of the chair so that the user can recognize and interact with it via its digital counterpart. Alternatively, if a sufficiently large dataset is available, a similar shaped geometric representation can be found by the retrieval model. To preserve the user's immersion, the reconstructed mesh's color and geometric details must be adapted to the VR scene. The optimization of the text-to-mesh neural style network is guided by 2D views of the stylized 3D mesh and the similarity against the target text in the embedding space of clip. Besides the text prompt describing a fitting material or genre, the target style can also be defined by an image, displaying a specific part of the VR scene, or a combined target modality of both text and image. We evaluate how well the stylized meshes fit into the VR scene by computing the clip cosine similarities of the renderings against the text prompt describing the VR scene, in this case the descriptive name Meadows. To superimpose virtual representations of real-world objects that frequently get moved, like office chairs, they need to be tracked. We use a model trained on the Objectron dataset, which estimates the 3D bounding box that describes the position, orientation, and dimension of the object. These parameters are then applied to the virtual representation to superimpose it, so it resembles the real object in all regards except for its appearance. By matching the style of the VR scene as well as the basic shape of the real object, the stylized and superimposed representation preserves immersion and enables the user to interact with the real object. We hope that our proposed AV pipeline inspires further research in the fields of reconstruction, style transfer, and superimposition to create AV scenes where the user can interact with most, if not all, real-world objects through their style-aware augmented virtuality embeddings.